Alright, so in this video I'm going to talk about buoyancy, just what it is, where it comes from, and how we use it in engineering. So buoyancy is a force from a fluid acting on an object. It's due to hydrostatic forces, and what that means is just if we have a fluid and if we have a block inside the fluid is kind of is pushing on this block in all directions, and this force that it's applying on it, these forces, they all kind of depend on how far deep into the water they are, or how deep into the fluid they are. They're depth dependent. And so if we just have this block, let's just say it has an area A and length L. These left and right forces, they kind of cancel out because, for it's depth dependent, right? It doesn't matter how far left or right you are. So for at any point along this face, there's an equal force in the opposite direction at that same depth. And so you can kind of say they cancel out. And for these up and down forces, well, like I said earlier, it gets stronger the deeper you get. So this bottom force is actually much stronger. And so you could say the net equivalent of this block, it's kind of just one upward force, because this upper one, or this one pointing up, is stronger than the one pointing down. And let's just do a quick derivation. So forces from each of these forces, well, they're kind of equal rho g h a. So the density of the fluid times gravity times how deep in the water it is times the area of that face it's kind of pressing on. And so if we just look at these top and bottom ones real quick, what we'll get is rho g a h plus L minus, because it's pointing down for the next one, rho g a h. When you do the math, you'll end up with is rho g h a L, and oh, sorry, no h, my bad. Sorry, I'll just write this again. You'll end up with rho g a L, and AL is the same as volume. So what you're really left with is force equals rho g v, and this is the magnitude for the buoyancy force. And like we said earlier, it just points up, so that's the direction of the buoyancy force. So now I'm just going to talk a bit more about this formula and each term. So the buoyancy force is equal to rho times g times v. So this rho, that just means the density of the fluid. So if we're in water, if an object's in water, or if it's in gasoline or ethanol or even air, because air is a fluid, they'll all experience different buoyancy forces. Same thing with G, depending on where we are. If we're on Earth or the Moon or Mars, it gives us different buoyancy forces. And for volume, the volume of the object does matter, but it's really the amount of the object that's submerged that matters. So if I have two objects that are the same volume and one is submerged and one is floating, the volume you'd use in calculating its buoyancy force is how much volume is submerged. So in this example, you'd use the total volume, but in this case, you'd only use the part of it that's submerged underwater for your volume factor in the buoyancy calculations. And so if you wanted to know why some objects sink or swim, well, buoyancy always pushes the object up, but there's also a gravity force. And so in this case, you could say that the buoyancy force is equal to the gravity force, and that's why it floats. But here, you wouldn't be able to say that. The gravity force would have to exceed the buoyancy force, and that's why it would sink. So that kind of just tells you if something's going to float or sink. You just compare the buoyancy force with the gravitational force. So next I'm just going to quickly talk about how this is used in engineering. We use it in boats. Sometimes if we have a block of mass or a block of metal, it just kind of sinks. But if we spread it out, well, now it takes up a much larger volume, so its buoyancy force goes up. And that's why large metal blocks are able to float. Yeah, thank you.